Woohoo! Welcome back. Today we're going to be working with integrals with trigonometry. Yay! With our friend Square Bear. And to start us off, I thought I would have a list of trigonometric facts. Now, before we get started, I want to point out that these can be very challenging problems. And between the last section we did, integration by parts, this section, which is the basic trigonometry, and what's coming in the next section, which is going to be something called trigonometric substitution, there's a lot of moving parts in all of these problems. And so I want to encourage you to be really gentle with yourself when you're going through these, because they're not as easy as I'm going to make it seem. And if you just faced one of these integrals on the street, it would be really hard to decide what tools to use. The goals of these sections are to provide you with a lot of different tools, but also an understanding that sometimes you try one thing, and if it doesn't work, you try something else. So don't assume that these are obvious and easy, but definitely do the practice and think to yourself, like, why would I choose this? And why would I choose this other thing? Okay, let's get started. It's going to be exciting. It's going to be so much. Square Bear is here to be there with us. Woohoo! And he's very excited because he can see there are squares already. So this list of facts about trigonometry includes all sorts of things. I'm going to move Square Bear over. Some basic truths about trig. Now, if you haven't taken trig, or you haven't taken trig recently, there are the half angle formulas or the double angle formulas. There are the addition, the sums and differences of angles. There's all sorts of interesting stuff going on. And so just keep in mind, we've got a lot of different formulas. And I would encourage you to keep a sheet like this available while you're doing your homework, so you can kind of quickly look to see if anything on the sheet matches the problem that you're working on. Okay, so let's go ahead and get started. Let me see if I can help you get some insight into some choices you could make. Okay, dum dum dum. We're going to start off with one where I'm asking you for the integral of sine of x cosine of x dx. The most basic thing to remember about sine and cosine are that they are derivatives of each other. And so if you say set u equal to sine of x, then du would be cosine x dx. And so you've got a very straightforward u substitution problem where you substitute u for sine x, and you've got the du here, the cosine dx, and then you just set it up as a u du problem, which when I integrate, I get u squared over 2 plus c, and that's equal to sine squared. And when you have sine squared, you put the 2 in the middle. It's kind of a weird shortcut that we do. Now, a lot of folks are going to ask me, well, what if I did it the other way? And this is where things start to get complicated, because it is possible to overthink these. It's also possible to underthink. Don't worry about the next one. But what if instead of setting u equal to sine, what if you decide to set u equal to cosine? Now, personally, I wouldn't want to do this because I know that the derivative of cosine is the opposite of sine, and then you end up with all these weird minuses running around. But let's say you did. You just decided to do it this way. Okay, if you set it up this way, then your integral is going to be there's the sine x and the dx, but it's not the opposite of sine x dx. So you have the opposite of u du, which again is going to give you u squared over 2 plus c. And already I can see a lot of folks going, oh, I don't know about this. Okay, and then if I go ahead and replug in, this is the opposite of cosine squared over 2 plus c. And the next question is this the same answer? That is a really good question. And let me check to make sure. Do I have some? Oh, I don't have any blank paper. Oh no! Pterodactyl, save us, save us. Where's my blank paper? There. That's not blank paper. That's blank paper. There we go. Okay. So, are these two the same answer? Because it would be very upsetting if two different techniques gave us two different answers for an integral. So let's go ahead. I'm going to give myself a little arrow there so we remember where we went. And then I'm going to write down sine squared x over 2 plus c versus the opposite of cosine squared x over 2 plus c. Okay, let's compare these. Are they the same answer? And I'm going to try to convince you that they are actually the same answer. They're not written the same way, and they're not exactly expressing the same things, but they are equivalent answers. So how am I going to show you that? Well, I'm going to point out that right up top, we've got this, the Pythagorean truth, the sine squared plus cosine squared equals 1. Which I have written in this sheet as sine squared equals 1 minus cosine squared x. Okay, so here's sine squared x over 2 plus c. That's got to be 1 minus cosine squared x over 2 plus c, right? Because instead of sine squared, I'm going to plug in 1 minus cosine squared. Okay, so that's going to be 1/2 minus cosine squared x over 2 plus c. And then I'm going to do something which you're either going to think is really cool or think is really obnoxious. You ready? I'm going to say these two are both constants. So this is really just the opposite of cosine squared over 2 plus a slightly different constant. Since we didn't specify what the constant was yet, this is an indefinite integral, so we don't know what the constant related to the original problem was. So, yeah, I'm going to claim this does match. And some of you are forever going to be thinking, I don't like that the 1/2 kind of got smushed in. And I'm going to say, that's okay. We can agree to disagree. But this is going to happen a lot with the problems we're doing in this section. There's going to be a lot of judgment calls, and you're going to possibly come up with an answer. And even if you're working with other people, they may come up with slightly different answers. And then the trick will be figuring out, did you get the same answer? And the truth of that is that this happens in math all the time. All the time, you'll be working on something and you'll realize that you've got two different answers and you're not sure if they're the same or not. So this is actually something I had a question for a colleague last semester. I had worked out a problem in a kind of a novel way and was asking them, what did they think? Because I got such a different answer. And it took us a few days to figure out that, yes, in fact, the two answers were equivalent. They just didn't look like each other. So this is an ongoing big issue with math, is Are these two things equal? And in this case, I'm going to tell you they are, but I understand if you feel uncomfortable about it. Okay, shall we go ahead? And the other answer is, which one should you choose, right? That's the more practical question for students. I don't care. I personally think this one's cleaner because there's no minuses running around. This feels very much like borrowing trouble when you start putting minuses into a problem. But if this is the way that makes sense to you and you can see your way through it, rock on, do that way. Okay. Now, second one. The second one, I think, is a little bit more obvious. In this case, I've got the integral of sine squared x cosine x dx. And this actually has a couple of different solutions. But given that we just did this one previously, I'm going to say that I think setting u equal to sine x and then du is cosine x dx, I think this is going to be the more obvious path forward, because then you've got u squared right there. Let me bring out my blues and my yellows. There's u. So that's my u squared. And here's my du. So that's going to be right there. And I'm just going to use a u substitution. The integral of u squared du, u cubed over 3 plus c, right? And then u was just sine, so this is sine cubed of x over 3 plus c. Kind of woohoo. A little bit, kind of a half of a who. Okay. Next up. This is that page. Aha. You guys ready? The paper might not be. I'm sorry, we can't go forward if the paper refuses to come over here. Come here. It's a shy piece of paper. Here, I'll bring in Square Bear. That makes everyone feel better. Hey, Square Bear, can you make them feel better? Sure. Arr. Yeah, that totally works. Everyone feels better when they've got a bear growling at them. Okay, this one's kind of interesting. I've got cosine cubed of x dx. Now, the problem with this is that I could set u equal to cosine, but then I don't have the du because I would need a sine, right? In order to do the u and the du like we've been doing, I have to have a sine and a cosine. And I only have one and not the other. But wait, presto changeo. I happen to know that this is equal to cosine squared of x times cosine of x times dx. What do you guys think? So far, so good? And then I happen to know that cosine squared is 1 minus sine squared. Right? Cosine squared is 1 minus sine squared. Sine squared is 1 minus cosine squared. So now I can rewrite this as cosine of x minus sine squared of x cosine of x, all dx. And I can see Square Bear's not impressed with me. I obviously have not given myself enough room with any of these problems, so I feel pretty bad about that. I'm so sorry, Square Bear. But if we go on to the next page, I've got, oops, sorry, Square Bear. I've got the integral of cosine of x minus sine squared of x cosine x dx, right? And then I can split this up. The integral of cosine x dx minus the integral of sine squared x cosine x dx. Okay, well, we've already done something very similar to this, sine squared, cosine squared. So I know that when I've got sine squared of x, cosine x dx, that's going to give me this sine cubed of x over 3 plus c. So right here, this is sine cubed of x over 3 plus c. And this is from the first page. And then what's the integral of cosine? Well, that one's pretty straightforward because that's just sine. Now, I could put another c here, but I'm going to consider that I've taken care of the constant there. Again, if you like to have a C1 and a C2 and bring them all together into a C3, that is fine. Functionally, you just need that one constant there to remind everyone, if you take a derivative to check it, we don't know what was there, because if there's a constant to begin with, if there was like a plus 10, when you take the derivative, it zeroes out. So it's just a reminder that there might be a little bit more going on, but that the functional part right there is what we've got. So what do you guys think? Not too bad, right? Okay, kind of okay. Yeah, okay. I can feel through the camera that some of y'all are like, we don't know. This is less mathy and more squishy. So what I want to do is, we're up at over 15 minutes, so let me take a break. There's a bunch of the homework that you can do right now that is actually just like these first few problems. So go ahead, try them out, see if they make sense, ask me questions, ask the tutors questions, and then give yourself a little break. You know, go out, touch some grass, pet an animal, you know, go out and have fun, play video games, dance around, sing, whatever it is that brings you joy. And then come on back, and I got more joy, because we're going to do other math. I know, what's more joyful than more math? But we're going to keep going with all of these interesting trigonometric equations and formulas. So, math on, woohoo.